The distance between two consecutive crests in a wave train produces a string in 5 centimeters. String is 5 centimeters. If two complete waves passes through any point per second, the velocity of the wave is 10 centimeter per second, 5 centimeter per second, 2.5 centimeters per second, or is it 15 centimeters per second. So we have the distance between two crests, that is the wavelength, that is given as 5 centimeters, and if two complete waves passes through any points per second, that is the frequency, which is 2 waves it is passing per second. So the velocity is given by n lambda. So n is 2 into 5, that gives you 10 centimeters per second. So the correct option is A. Question number 2. When a sound wave of frequency 300 Hz passes through a medium, the maximum displacement of a particle of the medium is 0.1. The maximum velocity of the particle is equals to 60 pi centimeters per second, 30 centimeters per second, 30 pi centimeters per second, or 60 centimeters per second. Okay, so basically here it is a sound wave of frequency n is given as 300 Hz, passes through a medium, the maximum displacement A, which is equals to 0.1 centimeters is given. Then the maximum velocity of the particle is, so Vmax we have to find, which comes after formula is A into the angular frequency omega. So we have A into omega, that is 2 pi by T, that can be A into 2 pi n. So as 1 upon T equals to n, that is the frequency. So A is 0.1 into 2 into pi into n, we have 300. The value comes out to be 60 pi centimeter per second, that is the velocity Vmax. So the answer is option number 8, 60 pi centimeters per second. Next one, the velocity of sound wave in air is 330 centimeter per second. For a particular sound in air, a part difference at 40 centimeters is equivalent to the phase difference of 1.6 pi. The frequency of the wave is 165 Hz, 150 Hz, 660 Hz, or 300 Hz. So the solution is, we have a velocity which is equals to 330 meter per second. Okay, for a particle we know the formula of the part difference. Part difference is equals to, we can write it in other way, it is phase difference is equals to 2 pi upon lambda multiplied by the path difference. Okay, so we have given the both, that is the part difference at 40 centimeters equivalent to the phase difference of 1.6 pi. So phase difference of 1.6 pi is equals to a part difference of 40. So the value of lambda comes out to be 50 centimeters, where lambda can be again converted, that is 0.5 meters we get. Okay, now we got the wavelength, we need to find the frequency. We know the velocity is equals to frequency into the wavelength. So the frequency will be V upon lambda, where V is 330 upon lambda we found out to be 0.5. So we get n is equals to 660 Hz. So option C is the correct option. The frequency of a rod is 200 Hz. If the velocity of the sound in air is 340 meter per second, the wavelength of the sound produced is 1.7 centimeters, 1.7 meters, 6.8 centimeters, 6.8 meters. So we have the solution. Here we have given the frequency n is equals to 200 Hz. Okay, and we have the velocity which is equals to 340 meter per second. Next we want to find the wavelength. So we know V is equals to n lambda. Also lambda is equals to V. Lambda is equals to, we can get as V upon n. So V is given as 340 upon the n will be 200. That comes out to be 1.7 meters. So option C is the correct option. Okay, next one. A stone is dropped into a lake from a tower 500 meters high. The sound of the splash will be heard by the man approximately after 11.5 seconds, 21 seconds, 10 seconds, or 14 seconds. Now here we have a stone which is dropped into a lake of certain height. That height is 500 meters. So we will find the time taken for the stone to reach the lake. So that T1 is equals to under root of 2h upon g. Okay, where we get the values 2 into h is 500 upon g, we can take it as 10. So the value of T1 comes out to be 10 seconds. So it takes 10 seconds for the stone to drop or to fall down on the lake. Okay. Next thing, now we'll find the time taken by the sound from to go from the lake to the man. Okay, that is the time 2, which is equals to the distance height upon the velocity of the sound. That is, distance is 500 and the velocity of sound in air is 340, so the value comes out to be 1.5 seconds. So the total time taken for the stone to drop and the sound to reach the man is total time t, that is t1 plus t2, that is 10 plus 1.5, that is 11.5 seconds. So option is the correct option. So when sound travels from air to water, which of the following remains constant? Velocity, frequency, wavelength, or all of the above? When the sound wave travels from one medium to the another medium, the frequency and the velocity will change. Depending on the medium, the frequency might decrease, increase, and the wavelength might decrease, increase, but the wavelength might decrease, increase, but the frequency of the sound will remain the same while traveling from one medium to the another medium. Next up, a boat by anchor is rocked by a wave whose crests are 100 meters apart and velocity is 25 meter per second. The boat bounces up in every, how much time it is? 2500 seconds, 75 seconds, 4 seconds, or 0.25 seconds. So we have a boat which is rocked by a wave whose crest are 100 meters. So we have lambda 100 meters, that is the wavelength is 100 meters, and the velocity is given 25 meter per second. Now we have to find how much by how many time, after how much time the boat will bounce. That is the t, which is equals to lambda upon v, that is lambda is 100 upon 25, that comes out to be 4 seconds. So the correct option is option C, 4 seconds. Sound waves transfer only energy, not momentum, energy, momentum, both energy and momentum. Sound waves, whenever the sound wave travels, they carry them with them the energy as well as the momentum they have. So whenever they travel, they transfer both energy and the momentum. So the correct option is D. The phase difference between 2 points separated by 1 meter in a wave of frequency 120 Hz is 90 degrees. The wave velocity is 180 meters per second, 240 meters per second, 480 meters per second, or 720 meters per second. So we have given the frequency n, which is equals to 120 Hz. Okay, we know the formula for phase difference. Phase difference is equals to lambda by 2 pi into the psi, which can be the theta. Here the phase difference is separated by a distance of 1 meter, which is lambda by 2 pi, and making an angle of theta, that is pi by 2. So solving this, we get pi by lambda by 4, 1, which is equals to, so lambda becomes equals to 4 meters. So we need to find the wave velocity. Velocity is equals to n into lambda. N is the frequency 120, lambda is the wavelength 4, so we get the answer 480 meters per second. So C is the correct option. When the sound is produced in an aeroplane moving with a velocity of 200 meters per second, horizontally its echo is heard after 10 to 5 seconds. If the velocity of the sound in air is 300 meters per second, the elevation of the aircraft is A 250 meters, B 1250 meters, C B 250 root 5 meters, C 1250 meters, or D 2500 meters. So basically we'll construct something like a triangle. Okay, O A C. Okay, the sound is produced in an airplane moving with velocity 200 meters per second. Horizontally its echo is heard after 10 to 5 seconds. So in order to travel the sound from O to C, it takes 10 to 5 seconds. So the distance travel, that is the OC, will be the velocity, that is 200 multiplied by 10 root 5. Okay, that is the time for the echo. We have when the sound is produced in an aeroplane moving with a velocity of 200 meters per second, horizontally its echo is heard after 10 to 5 seconds. If the velocity of sound in air is 300 meters per second, the elevation of the aircraft is 250 meters, 1250 meters, 250 root 5 meters, or 2500 meters. Suppose this is the ground level and this is where the aeroplane is flying from the path B to C. The echo is heard across the path B to C, so we take the center of that as O. So the distance traveled by the echo from C to O is half of the total time. That is half of the total time, that is 10 root 5 seconds for the echo. That gives you 5 root 5 seconds from O to C. Now we will calculate the distance between O to C. Distance between OC is the velocity, that is the sound is taking with a velocity of 200 multiplied by the time taken, that is 5 root 5. That comes out to be 2236 meters. Okay, 2236 meters. Then we'll calculate the distance between AC. So AC is velocity of the sound, that is given as 300 meters per second multiplied by again the time taken for the echo, that is 5 root 5. That gives you 3354 meters. Okay, now using the Pythagoras theorem, we get the distance OA is OA square is equals to under root of, okay, OA can be taken as under root of this is AC minus OC square. Okay, so that comes out to the value 2500 meters is OA. So D is your correct option, 2500 meters. When the temperature of an ideal gas is increased by 600 Kelvin, the velocity of the sound in the gas becomes root 3 times the initial velocity in it. The initial temperature of the gas is minus 73 degrees Celsius, 127 degrees Celsius, 27 degrees Celsius or 327 degrees Celsius. So basically we know the equation for the velocities of the gas in temperature, that V is directly proportional to root T. So the initial velocity upon final velocity upon the initial velocity will be the change in the temperatures, T2 upon T1, where T2 is the original temperature plus the gas, ideal gas, the temperature is increased by 600 Kelvin upon T1. Here we know that the velocity of the sound in the gas becomes root 3 times the initial velocity. So V2 upon V21 is root 3 is equals to T1 plus 600 upon T1. The value for T comes out to be 300 Kelvin. So T is equals to 27 degrees Celsius. So option B is the correct option. The frequency of a sound wave is n and its velocity is v. If the frequency is increased by 4n, the velocity of the wave will be v, 4v, 2v or v by 4. Here the velocity of the sound is independent of the frequency. So therefore it is the same for v and for 4n, for the frequency to be n or for 4n. So the correct option is v. The velocity will be v even though the frequency change, the velocity of the sound will be the same. The speed of sound at constant temperature depends upon pressure, density of the gas, above both or none of the above. Speed of sound at constant temperature does not depend on pressure, neither it depends on the density of the gas. So it is none of the above. What will be the wave velocity if a radar gives 54 waves per minute and the wavelength of the given wave is 10 meters? So options are 4 meters per second, 6 meters per second, 9 meters per second or 5 meters per second. Here the frequency, we write its solution. The frequency n is given as 54 waves per minute, that is 60 seconds. Okay, 54 upon 60, and the wavelength lambda is given as 10 meters. We need to find the velocity v, which is equals to n lambda, that is 54 upon 60 into 10, that is 9 meters per second. So v is equals to C option, 9 meters per second. A man stands in front of an hillock and fires a gun. He hears an echo after 1.5 seconds. The distance of the hillock from the man is, the velocity of the sound in air is 330 meters per second. The distance we have to calculate, the options are 220 meters, 247.5 meters, 268.5 meters, 292.5 meters. Okay, solution. If suppose the distance between the man and the hillock is d, then he will hear the sound once he will hear the echo once the sound hits the hillock and returns back to him. That will, the distance will be 2d, which is equals to v into t. So d will be equals to velocity into time upon 2. Here the velocity is given to be 330 multiplied by time taken to hear the echo is 1.5 upon 2. The answer comes out to be 247.5 meters is the distance. So option B is the correct option, 247.5. The speed of a wave in a medium is 760 meters per second. If 3600 waves are passing through a point in 1 minute, in the medium in 2 minutes, then the wavelength is 13.8 meters, 25.3 meters, 41.5 meters or 57.2 meters. Okay, so here we have we will find the frequency of the waves, that is 3600 waves are passing at a point in the medium in 2 minutes, that is 2 into 60, the answer of the frequency is 30 Hertz. Okay, next we have the speed, velocity, which is given to be 760 meters per second. We need to find the wavelength, lambda, which is equals to V upon frequency, that is V is equals to 760 upon 30, that gives out to be the value 24. Okay, wait, that will give you the value 25.3 meters. So option B is the correct option. The frequency of a tuning fork is 384 per second, and the velocity of the sound in air is 352 meters per second. How far the sound has traveled while the fork completes 36 vibrations? Options are 3 meters, 13 meters, 23 meters and 33 meters. Okay, so here we have the wavelength, lambda is equals to V upon L. The velocity given is 352 and the frequency of the tuning fork is 384. That is 352 upon 384 is the wavelength, is the wavelength during one vibration of the fork the sound will travel. Okay, that is the during one vibration the sound will travel 352 upon 384 second, the 352 upon 384 meters. Okay, that is the wavelength. So during 36 vibrations the distance travel will be 352 upon 384 into 36. So the answer will be, lambda comes out to be 33 meters. So D is the correct option, 33 meters. If V1 and V2 are the velocities of sound at the same temperature in two monoatomic gases of densities ρ1 and ρ2 respectively, ρ1 upon ρ2 is equals to 1 upon 4, then the ratio of the velocities V1 and V2 will be 1 is to 2, 4 is to 1, 2 is to 1 or 1 is to 4. Okay, now the solution here, we know that at constant temperature, at the same temperature and the same pressure, the velocity is inversely proportional to the root of the densities. So V1 upon V2 will be ρ2 upon ρ1 under root of ρ2 upon ρ1. So we have the ratios of ρ1 upon ρ2 is 1 upon 4. So ρ2 upon ρ1 will be 4 upon 1. That comes out to be 2 is to 1, that is V1 upon V2. So the correct option is C, 2 is to 1. Now, the temperature at which the speed of sound in air becomes double of its value at 0 degree Celsius is 273 Kelvin, 546 Kelvin, 1092 Kelvin or 0 Kelvin. So we know that V is directly proportional to under root of T. So we can have V1 upon V2 is equals to under root T1 upon T2. Similar way, I can write T2 is equals to T1 of V1 upon T1. Okay. The temperature at which the speed of sound in air becomes double of its value at 0 degree Celsius is 273 Kelvin, 546 Kelvin, 1092 Kelvin or 0 Kelvin. Here we know that V is directly proportional to under root T. So I can write V2 upon V1 is equals to under root of T2 upon T1. So the velocity of one when the velocity becomes double of its initial velocity at 0 degree Celsius is, that is, I can write T1 is equals to, or I can write T2 is equals to T1 V2 upon V1 the whole square, that is T2 is equals to T1 at 0 degree Celsius, it will be 273 kelvins multiplied by the velocities, which is when the velocity becomes double, so 2 square, that is 273 into 4, that gives you the answer 1092 Kelvin. So C is the correct option, 1092. It takes 2.0 seconds for a sound wave to travel between the two fixed points when the day temperature is 10 degrees Celsius. If the temperature rises to 30 degrees Celsius, the sound wave travels between the same fixed point is 1.9 seconds, 2.0 seconds, 2.1 seconds or 2.2 seconds. Okay, so we know that let the distance, suppose the distance between the two fixed points is t, that is small d will be the distance. So we know that the time taken will be distance upon velocity. So also this velocity is directly proportional to time t. Okay, so we have t1 upon t2 which will be equals to v2 upon v1 according to this relation, which is which is again equal to T2 upon T1, the small absolute temperature, the large temperatures. So T1 upon T2 is equals to under root of T2 upon T1. So we get T1, the time given is 2 seconds, upon T2 we need to find for the distance D1 for the distance for the temperature. The rise for the temperature is 10 degrees and here it is 30 degrees Celsius, that is under root of T2, that is 303 degrees, 303 upon 283 Kelvin, that gives you T2, that is under root of 303 upon 283 multiplied by 2. So that gives you the answer 1.9 seconds T2. So A is the correct option, 1.9 seconds. Okay. If the phase difference between the two sound waves of wavelength lambda is 60 degrees, then the corresponding part difference is lambda by 6, lambda by 2, lambda by 4, 2 pi or 6 by lambda. Okay. Next, the solution here is, we know that here we are having the part difference and the phase difference. So the part difference delta x for a given phase difference delta is given by, we can have delta x equals to lambda upon 2 pi into del. Okay, so here in this given situation we have del, that is the wavelength, that is 60 degrees, we can convert it as pi by 3. Okay, so delta x is equals to lambda by 2 pi into pi by 3, so the value comes out to be pi by 6. So the part difference, so the phase difference is given as pi by 6. The part difference, the corresponding part difference is pi by lambda by 6. So A is the correct option, lambda by 6. The source of sound of frequency 600 Hz is placed inside the water. The speed of sound in water is 1500 meters per second and in air is 300 meters per second. The frequency of the sound recorded by an observer who is standing in air is 200 Hz, 120 Hz, 3000 Hz or 600 Hz. The frequency of the sound does not change with the medium. It remains a constant. So whether it is inside the water or in there, the frequency of the sound of the source, if it is 600 Hz, it will remain 600 Hz. So the option is D, that is 600 Hz, because the frequency of the sound does not change with the medium. If the temperature of the atmosphere is increased, the following character of the sound is affected: amplitude, frequency, velocity or wavelength. If we increase the temperature, we know the formula V is directly proportional to T. So as the velocity increases, the temperature will also, as the temperature increases, the velocity will also increase. So the factors which will affect the sound wave is the velocity C. Water waves are longitudinal, transverse, both longitudinal and transverse, neither longitudinal nor transverse. Water waves behaves both longitudinal. Water waves are basically both longitudinal and transverse in nature. So they can travel perpendicular to the direction of propagation or parallel to the direction of propagation. So they are both longitudinal and transverse. So C is the correct option. Now water waves are both longitudinal and transverse. Ultrasonic signal sent from sonar returns to Earth after reflection from a rock after a lapse of 1 second. If the velocity of the ultrasound in the water is 1600 meters per second, the depth of the rock in the water is 300 meters, 500 meters, 400 meters or 800 meters. So here let D be the distance of the sound reaching from the sonar and then hitting the rock and then returning back. So the distance has been calculated twice, so it is 2D is equals to V into T, where D becomes again equals to V upon V into T upon 2, where D will be equals to velocity, which is given about of the sound is 1600 multiplied with the time taken is 1 second upon 2. So the answer is 800 meters is the distance. So D is the correct option, 800 meters. What is the phase difference between the two successive crests in a wave? Pi, 2 pi, pi by 2 or 4 pi, where phase difference is psi, which is equals to 2 pi upon lambda, and the phase difference between two successive crests, the distance between two successive crests is the wavelength, that is the lambda. So we get the phase difference is 2 pi. It is 2 pi. The correct option is C. It is 2 pi. A big explosion on the moon cannot be heard on the earth because the explosion produces high frequency sound waves which are inaudible. The sound wave requires a material medium for propagation. Sound waves are absorbed in the moon's atmosphere. The sound waves are absorbed in the earth's atmosphere. Basically, to produce the sound waves, you need a medium. In order to hear the sound waves, we require a material medium. So, the sound waves requires a material medium for propagation. On the moon, there is no such medium for the transfer of the sound waves. So, the sound can't be heard because of no material medium. Hence, the sound wave requires a material medium for propagation. Sonar emits which of the following waves? Radio waves, sonic waves, ultrasonic waves, or infrasonic waves. Basically, the sonar technology uses ultrasonic waves. It is sound navigation and ranging system. That is the ultrasonic waves which they are using. So the correct option is C.